Now that we fundamentally understand what agentic reasoning is, let us examine how a single agent actually operates under the hood. Before we talk about how agents learn or how they work collaboratively in teams, we need to understand the bedrock capabilities of an individual agent. When a large language model becomes an autonomous problem solver, it moves from being a passive text generator to an entity that formulates strategic plans, explores diverse alternatives, and executes grounded operations in the real world. We call this foundational agentic reasoning. This foundational workflow is essentially an interconnected cycle of three core components: planning, search, which is often referred to as agentic RAG, and tool use. Let us break each of these down in detail. The first and arguably most critical step is planning. It is not enough for an intelligent agent to just know facts. It must figure out how to practically achieve a given goal over multiple steps. This involves decomposing a highly complex abstract goal into a sequence of tractable, actionable subtasks. In the early days of LLMs, we saw simple, linear reasoning, like standard chain of thought. But true agentic planning is much more robust and nonlinear. The research categorizes two main paradigms for agentic planning. The first paradigm is in-context search. This is where the model uses its context window to iteratively explore different possibilities, essentially searching through a vast thought space. The React framework is a classic and highly influential example of this. The agent continuously interleaves generic thoughts, concrete actions, and environmental observations to guide its progression toward a goal. Another powerful example is Tree of Thoughts, where the model explores multiple divergent reasoning paths simultaneously, structured like a decision tree. It evaluates nodes, backtracks when necessary, and explicitly decides which path is most promising to pursue. The second major paradigm is optimization-based planning. Here, the model learns to plan through training techniques like deep reinforcement learning. It is not merely prompting the model to think step by step at inference time. The model's actual neural weights are updated based on the ultimate success or failure of its generated plans. This internalizes the planning capability, making the agent inherently better and vastly more efficient at long-horizon tasks over time. Our second core component in foundational agentic reasoning is search. We are all likely familiar with Retrieval-Augmented Generation, commonly known as RAG. Traditional RAG is essentially a one-shot process. A user asks a question, the system blindly retrieves a few top documents based on vector similarity, and the LLM summarizes those documents. Agentic RAG, however, fundamentally turns retrieval into a continuous, decision-driven process. The agent actively decides when it genuinely needs more information, exactly what specific query to search for next, and whether the retrieved evidence actually answers the core question. It can rewrite and refine its queries if initial results are poor, aggregate and combine information from multiple disparate sources, and independently decide when to stop searching because it has gathered sufficient evidence. Some advanced systems even perform complex multimodal search, seamlessly combining text retrieval with inspecting visual documents, images, or video representations to synthesize a comprehensive, grounded answer. Finally, an agent needs to act on its formulated plan and retrieved context. This is where the third capability, tool use, comes into play. An agent without tools is like a highly intelligent brain trapped in a jar. It can think, but it cannot affect the world. Tool use connects the agent's internal reasoning loop to external functional systems. This could mean generating and executing a block of Python code to precisely solve a complex math equation, querying a massive SQL database for real-time analytics, or even autonomously controlling a web browser to navigate the internet. What makes this tool use specifically agentic is the degree of autonomy. The agent parses its environment, autonomously decides which specific API to call from a massive library, formats the complex JSON arguments required, and critically, interprets the raw result. If a tool fails, say an API returns a 400 bad request error or the generated Python code throws a syntax exception, an agentic system does not simply crash and give up. Instead, it uses that exact error message as highly informative feedback, reflects on its mistake, revises its code or arguments, and tries again. This continuous, resilient loop of execution and verification is exactly what transforms abstract theoretical reasoning into concrete, grounded action in the real world.